so what we have is we have okay, an object of mass m hanging from a spring, and there's been a motion detector is placed before the object, and it will create a graph of the position versus time. So in the first experiment, the object was pulled down 1 centimeter, released from rest, and obviously it oscillates up and down, like shown. And then the following two graphs are from experiment 2 and experiment 3, and we want to look, just based on what the position versus time graph looked like, what changed in each of the following experiments. So number 1 is like our baseline, right? This is what happened the first time. How did the rest compare, or how have they changed from the first one? So if you look at experiment 2, compared to experiment 1, it still has the exact same period, right? It completes one oscillation in the same amount of time. The only difference is that you have a greater amplitude. And remember, this is just the position versus time, so it's not telling me, like, if there's more energy, etc. Actually, it would be more energy because kx squared, you have a bigger x. But what it's telling me directly is just that you have a greater position at the beginning and then like at the ends, or not the ends, but like as it goes up and down. So instead of being pulled 1 centimeter like this, now it's being pulled down 2 centimeters. So I said that this was pulled down 2 centimeters and released from rest. And then it kept the exact same period. So if we look at our period equation, the square root of m over k, so if it's keeping the same period, that means m and k probably stay the same. So I'm going to say, so the same mass and spring constant. Now it's possible that you could have like doubled the mass and doubled the spring constant, which cancels out, but we probably kept the same mass and same spring constant because period did not change. Now in graph 3, again, we're comparing back to experiment 1, so if we just look, it's hard to, whatever. So compared to experiment 1, now my amplitude is back to the 1 centimeter, but I have a much shorter period. Now it takes way less time to complete one oscillation than before. So now it's going to be pulled down 1 centimeter, but because you have a shorter period, we know that either my mass or my spring constant has changed. So we have to look at the equation because we want to put as much detail as possible. So if you have a shorter period, that means you have less mass. So we either have less mass hanging on the spring now, or it could be that you have a greater spring constant, because less mass on top would mean less period, or more k dividing by a greater number would mean a smaller period. Or you could have a higher spring constant, a stiffer spring. So you either replace the mass with a smaller mass, or you replace the spring with a spring that's stiffer, that has a higher K. And then I saw a couple people in class today put like the numbers, because in fact you have half of the period, right? In this one full oscillation took this much time, you get 2 oscillations, so that's, you can see, now like half the amount of time to do 1 oscillation. So if you want to have half the period, we do not want to half the mass or double the K, because that is inside of square root, so it would be have to have 1/4 the mass or 4 times the K string constant, because then when you have either a 1/4 right here, that would get square rooted and have a factor of 1/2, or if you just had 4 on the bottom, that would be square root of 1/4, which would be 1/2. So either 1/4 the mass or 4 times the spring constant. You don't have to give like the actual numerics, just saying like you either decrease the mass or increase the spring constant because you have a shorter period would be enough, but I just wanted you to see that it's not actually a factor of 2, it's a factor of 4 inside the square root. Alright, object is attached to a spring and oscillates with amplitude A and a period T as shown. Sketch the following graphs, but also I asked where is the block instantaneously at rest. So I actually asked where, I meant like when. So you could either say at X is positive A or at negative A. Or you could have said at T, if this is period T, then this would be like 1/2, so this would be T over 4, and this would be 3/4 T. So 3t over 4. So at t over 4 and 3t over 4, those would be the times. These would be the actual positions where the velocity is instantaneously at rest. And you can't just say, like, because it's farthest, like, you have to give actual physics reasoning other than, like, oh, because you always said when it's the farthest, it's at rest. So lots of different ways you can say this. One way, so one explanation would be that is when the velocity goes between positive and negative, right? It's turning direction. So here it's changing direction. You're going from a positive velocity to a negative velocity. So v must be 0 for an instant in between positive and negative. That's one way you can explain it. You also can think about it in terms of energy. At the maximum displacement, so at the maximum displacement or at the amplitude, you have all potential energy, which means that kinetic energy is 0, so your velocity would have to be 0. Those would all work. I'm sure there's another way you can explain it that would also be valid, but make sure you're actually making physics points, not just stating something that, like, oh, because it's always 0 at the top. Or you also, another way is you could say that velocity is the slope of a displacement versus time graph. And then the slope at this point would be a flat slope, so a slope of 0. That's the third way you could explain it. All right, sketching the following graph. So for the graphs, I start with, like, where is it 0? So we just said that velocity would be 0 at these 2 points. So that would be t over 4 and 3/4 t, so that would be 0 here and here. And then now it's just filling in the wave, but you have to be careful, like, do I start positive or negative? So in this first, like, fourth of the period, I'm going up, so I start with a positive velocity, which means that these need to be positive values, and then I start going down, which means then it becomes negative values. So it would start positive, and then be negative up until this point right here, and now it's going up again, so that would be a positive velocity. So your velocity graph should look like this. And these correspond to, like, your maximum velocities. Your acceleration graph. So acceleration, you're going to have the greatest acceleration at the greatest displacements because acceleration goes with force and force is kx. So I know that my acceleration would be 0 where my force is 0. When my force is 0 is at the x is 0, equilibrium. So I'm going to put my 0 points. So acceleration 0 is when displacement is 0. But it's not going to look the exact same because if you have a displacement in the positive direction, so let's say you have a spring like this at equilibrium and I pull it to the right. When I pull it to the right, it feels the force to the left. It's going to accelerate back to the left. So when I have a positive displacement, that's a negative acceleration. And when I have a negative displacement, that's a positive acceleration because it's always trying to go back to equilibrium. And then when it's at equilibrium, there is no acceleration because it's at equilibrium, which is why these are then 0. Potential energy, so potential energy is 1/2 kx squared, so it depends on the position. So when your position is 0, your potential energy is 0. So plot these, and then you don't have to worry about positive or negative because energy can't be negative; it doesn't have direction. So we'll just go like this. And then your kinetic energy, you can think about as just the opposite of this. Or you can think about kinetic energy is 0 where your velocity is 0. So that would be 0 and that would be 0. And then it's maximum when your velocity is maximum. And then this is negative velocity, but when you square negative with the v squared equation, you're going to get positive, so positives. And then this is the exact flip of the, this one is the exact flip of each other, actually. So that's good because they would add up to the same total energy, same mechanical energy. Right, now we have a new object and it has a greater mass placed on the spring and it still oscillates with the exact same amplitude as before. So this graph, like still the same A and negative A, but now with the greater mass, I want to know how the following graphs will change. Where V max, A max, US max, and KE max, and T are all the original maximum values. So these values are just saying, like, these are the same from before, so how does the new value compare? Is it more max value or max velocity less? Is it a longer period, shorter period, same period, etc.? So I'm going to start with period first because that affects all of my graphs. So if you look at a mass on a spring period equation, that's square root of 2 pi squared of m over k. So if I increase the mass, so more mass is going to mean a bigger period or a longer period. Because this is a direct relationship, more on top is going to make this one greater. So all of my graphs are going to be stretched out. And then now I'm going to think through, so that's like telling me like the x-axis almost. Now I need to look at like my values on the y-axis. So let's think about the maximum velocity. It's easiest to come up with an expression because then you can just look at your expression and say like, oh, what does this do? Well, think about it. Your maximum velocity is when it has all kinetic energy. That all kinetic energy starts or comes from the energy at the start, which is the potential energy, the spring energy. So you've got 1/2 kx squared equals 1/2 mv squared. The halves cancel out. If we're talking about the maximum velocity, then we need to be talking about the maximum x, right? You only have the maximum velocity at equilibrium. You have only potential energy when it's at the amplitude, the very end. So I'm going to use A right there. And then divide your mass over. And then Vmax is just the square root of k squared over m. So I kept the exact same k, and I'm keeping the exact same m, or not, sorry, the exact same a, because it says the same amplitude, same spring is the same spring constant, but now I'm dividing by a greater number, so that's why my velocity should be less. So you have the same k and a, but more mass is going to give you less Vmax. So my graph compared to before where it was at Vmax, now I'm less than that original value. So I'm going to start here, and I'm still going to follow the same shape, but I'm not going to go down as far because my max values are now less. And I said it was a longer period, so one full oscillation will take more time compared to the period t from before. So, and we don't know exactly how much time, so we could just do something like this. It's clear that this is taking more time, and it's clear that your values are literally less than your Vmax values from before. Now, acceleration. So again, we know the longer period, that's going to be true for all of these, because for any oscillation it will take more time. Now I'm thinking through the values. So think about your acceleration. Well, we just use F equals ma. Net force equals mass times acceleration. So divide the m over, your net force over your mass is going to give you your acceleration. Well, if you were to draw a free body diagram, you've got like mg, you've got the normal force, and then you've got the spring force, right? Depending, it's going to change directions. This is if it's pulled to the right, it's got a spring force to the left. So my net force at any given point is just the spring force. So kx over m equals a. If I'm looking at the maximum acceleration, well, the maximum acceleration would be at the points where it's farthest from the equilibrium, because force directly depends on the displacement from equilibrium x. So then your maximum displacement, your maximum displacement and your maximum force are going to occur at x equals a. So Ka over m equals the maximum acceleration. Again, you have the same K and A, but you're dividing by a greater mass. So you now have a less maximum acceleration, a lower maximum acceleration. So I'm going to go back to my acceleration graph. I started at 0, and then I'm going to follow the same exact shape, but now it's spread out more and it's lower values. Now your potential energy you start with is 1/2 k amplitude squared. So this is the potential energy at the start. You're keeping the same k, you're keeping the same a, so then this is going to be the same value. And again, just a longer period because the reasoning stayed here. So I started with 0 potential energy, and it went like this. You'll notice I'm saying like this is the start. So this, I just assumed this was a graph of like oscillations, and it just happened to say like t equals 0. They started when it was passing through the equilibrium, but clearly like this would be kinetic energy, or like start with kinetic energy. But your t equals 0 doesn't really matter. You only have kinetic energy because it was pulled and then released, if that makes sense. So this is just saying like I picked at some random time for t to be 0, but you only have the kinetic energy because you pulled it and released it. So that would be the same, and then your kinetic energy is going to have the same amount, because if you start with the same amount of potential energy, you have to start with the same amount of kinetic energy, and then that would look like this. So same value, you want to make sure it's obvious that it's going up to the same amount, not lower, like these were clearly lower. If it was higher, make sure it's higher. So it's the same value, but then spread out over more time. Now if you're sitting there and you're like, wait, 1/2 mv squared equals your kinetic energy, and you just increase the mass, how does this not increase? Well, we just said up here that your velocity would actually decrease. So these end up balancing out to keep this the same. So the justifying any changes you would or would not make. So like for this one, we said that it would be more spread out, it would be a longer mass because of this. And then we said that it would be a less max value because of this reasoning. Here we said it was a less max value for this reasoning, and then the longer t goes for all of these, really. And then here we use this, so you're keeping the same k and same a to say this would be the same. Your explanation here is your ke comes from the US max, so this would have to stay the same as well. So we changed the values here, and period for all of them. Here we did not change the values, and we showed, or we explained that this stayed the same. And what would your kinetic energy of the block look like if the surface was not frictionless? Well, it would start to lose kinetic energy, so it would start with some whatever kinetic energy it started with, but then the next one would be less, and then the next one would be less if you were to like continue on until it gets to 0. Depending on how much friction, that would tell you like how quickly it dies off, but over time it would definitely lose less and less of its kinetic, it would lose more and more of its kinetic energy so that your maximum then would finally go to 0. Alright, we've got a pendulum of length L with a bob of mass M on the end, and it's released from some height h. The pendulum oscillates with a period of t, and it reaches a maximum speed of V max, max kinetic energy, and a frequency f. The same pendulum is released from a height greater than h. How would the following quantities be affected? I've heard people today, they're like, oh, a greater h is longer. That is not true. If I have this pen, let me zoom out. If this pen is my pendulum, and I like have it like this, and I release it, and it oscillates back and forth, or if I release it from a higher height and let it oscillate, the length of my pen has not changed. You are just changing the height that it's dropped from. Like, that would be like the amplitude. So that would be like for the spring, instead of going to A, you go farther than A. That's all that's changing is the amplitude. The height here being how far away from the equilibrium, how high above equilibrium it's placed or it's pulled up before it's released. The length not changed at all, right? You would have to have literally like cut your pendulum in order for the length to change. Okay, so we are changing only the amplitude. So you're increasing the amplitude and everything else is staying the same. And we want to know what's going to happen to your period. Well, period is 2 pi square root of m over k, not m over k. Ooh, we're talking about a pendulum, L over g. We haven't changed the length of the pendulum. As long as we're staying in the same spot, we haven't changed the acceleration due to gravity, so this is going to be the same. And we have to justify our answer. If it's giving us this room, we've got to write like at least a sentence here. So I would say that your period of a pendulum only depends on the length of the pendulum and the acceleration due to gravity. So the height, or the amplitude, has no effect on period. Right, if you're looking, you can write this equation off to the side. Like, the only thing that matters is length and the g, acceleration due to gravity. So the height that is dropped from, or the amplitude, has no effect on the period t. Now my new maximum velocity. It's telling me both to answer qualitatively and quantitatively. So like, this would be explaining using concepts. This one is explaining like using an equation. Let's start with the quantitatively. That's what I like to start with. So, well, not always, but in this case, I'm feeling it. So quantitatively, well, your maximum velocity, if you think about it, if you were to draw this pendulum and you release it from some height h, and then it goes to back and forth like this, well, your maximum velocity is going to happen right here because that is where you have the most kinetic energy. In fact, all of this gravitational potential energy just went into kinetic right here. So I can find that maximum speed pretty easily if I just use conservation of energy. So I'm going to start with all potential energy, but gravitational potential, because we're not talking about a spring, we're talking about how high above the ground, and that's going to go into all kinetic energy. So this is mgh, and this would be 1/2 kx squared, not kx squared, mv squared. And then you'll notice that my m's cancel out here. I would multiply the 2 up, so 2gh equals v squared. So the maximum velocity is going to be the square root of 2gh. So the quantitatively explanation is really easy. If Vmax is square root of 2gh and you increase h, you increase the Vmax. So there's my quantitative explanation. You use the equation and say, okay, bigger h, bigger Vmax. Now your qualitative is that you can say, okay, and this is really basically explaining this math in words, not necessarily the math, but these relationships in words. So you are now starting with a greater gravitational potential energy because you're starting higher. So if you start higher, you now have more gravitational potential energy, which means so you'll have more kinetic energy at the bottom. Careful here, because what a lot of you are going to want to say is like, oh, if you have more kinetic energy, it goes faster, which isn't necessarily true, because if I had increased the mass, then I would be increasing the UG, but not and increasing the KE, but not increasing the velocity, because see how the mass is canceled out here. So what I would say is you have more kinetic energy with the same mass, that means a greater velocity. So more kinetic energy with the same mass means greater velocity. And if you want to just like point to this, this is kind of quantitatively, but just pointing out this reasoning, right? If this increases and this stays the same, then this would have to increase as well. All right, my new maximum kinetic energy, well, we kind of already answered it up here, but that would, oh, I didn't actually answer. So increased Vmax would be faster than the original Vmax. All right, and then my new maximum kinetic energy, we started talking about it right here. So we would increase again. Quantitatively, I would just say, okay, potential energy is mgh, so if you increase h, you increase ug. And then your kinetic energy at the bottom is just the ug at the top, right? So my kinetic energy at the bottom is mgh. That's probably where you want to write those relationships, because this is the potential energy at the top, kinetic energy at the bottom just comes from the potential at the top, because at the bottom you have no potential, at the top you have no kinetic, and then that means your kinetic energy at the bottom is just the mgh. And if you increase h, you would then increase the kinetic energy. Sorry, I should have done that at the end instead of from the beginning. Now your qualitative answer is that now with a higher height means you start with more gravitational potential energy. The kinetic energy at the bottom of the swing comes from the potential energy at the top, so the KE at the bottom would increase. And the KE at the bottom is your KE max. And your frequency of oscillations, so frequency is 1 over the period. We said the period would stay the same, so your the height that we're changing, so height had no effect on the period, and frequency is 1 over the period, so if you have the same t, you'll have the same f, so same as the original f. Okay, and then again we have a pendulum with a bob, like length L, bob of mass m on the end, released from height h. The pendulum oscillates at the period t, reaches all these maximum values, etc. The same pendulum is now released, same height now, but now we're on the moon. Which of the following quantities will be affected? Well, if I go to the moon, The moon has a smaller acceleration due to gravity, or a smaller g. So I'm saying, what does a smaller g do to all of the following? So period, well, period for a pendulum is 2 pi square root of L over g. So if I decrease this value right here, so if you decrease this, if you have less acceleration, so, and you need to point out, like you have less g on the moon, that's going to be like, first point is like, I know that g is smaller on the moon. So if I'm dividing by a smaller number, I'm going to get a greater period. So your answer is going to be longer, and you need to make sure you explain this. So you can either talk about this is an indirect relationship, so decreasing g is increasing t. That's one way to go for it. T and g are inversely related. So decreasing g will increase t. Or you could say dividing by a smaller g will give a greater t. Those are basically saying the same thing, so either one or the other. You're saying g is going to be smaller here, and if I have a smaller g, I must have a longer t based on this equation. So longer period than the original. Now your new maximum velocity, and we want to use quantitatively. So we are starting with gravitational, goes to kinetic, that's mgh, 1/2 mv squared. Masses cancel out, 2gh equals v squared. Your maximum velocity is the square root of 2gh, or you could have just pulled it from before, because we already did this on the last one. All right, so now we are again decreasing g. This is a direct relationship, so if you decrease g, you are decreasing the maximum velocity. So your answer is that it's going to be slower than the original velocity, original maximum velocity when you're on Earth. And then your qualitative is that you, on the moon, which has a smaller g, not moon, smaller g, you have less potential energy at the start, even though it's the same height and the same mass. If you decrease g, right, you're decreasing the potential energy. So you'll have less kinetic energy at the bottom of the swing. So, we'll just start a new sentence. So less KE with the same mass will be slower Vmax. So less maximum kinetic energy, but keeping the same mass will be slower. And the reason I said with the same mass is you can have less kinetic energy but have the same speed if the mass decreased. But mass stayed the same, so if this is your equation, 1/2, and this decreased, but this mass stayed the same, that means the velocity had to decrease. Okay, the new maximum kinetic energy on the moon, well, we kind of already just said this. So your maximum, what I would say for the quantitative is that your KE max at the bottom is just equal to your potential energy max at the top, or the start. So that means your KE max is just the mgh. If you decrease g, you're going to decrease KE maximum. And then basically just explaining this in words. So you are starting with less gravitational potential energy at the start because you have a smaller acceleration due to gravity, smaller g. So you'll have less KE max at the bottom of the swing. So basically the same reasoning here, but not relating it to speed, just relating the energies. One thing to be careful with here is some of you are going to want to be like, oh, kinetic energy, 1/2 mv squared, well, that doesn't depend on g. So careful, because yes, this equation doesn't, but this kinetic energy that you have depends on the potential energy you started with, because energy is conserved, and the potential energy you started with depends on g. All right, and then the new frequency. So frequency is 1 over the period. So we just increase the period. So if you have a longer period, that means you're going to have a less frequency, because t and f are inversely related. So increasing t is going to decrease f. Or you could say dividing by a greater number is going to give me a smaller frequency. Or you could talk about like the actual definitions. So T is your period, the time for one. So if it takes it longer, so I'll write this one too. So if the time it takes for one oscillation is increased, then you will have, not you, but you'll, whatever. There will be less oscillations per second. Because the definition of frequency is the number of oscillations per second. Well, if it's going to take longer for one full one, then that means you get less of an oscillation each second. So then your answer is, your F is less than the original F.